So from last video, we saw that for each of these eigenspace, these finite dimensional eigenspace of this compact Hilbert-Schmidt integral operator T, the eigenspace is going to be inside the E, okay? And using the spectral theory, we know by the spectral decomposition, the space is going to be decomposed as a bunch of eigenspace for T, and also these are some finite dimensional ones as long as the eigenvalue is non-zero. And of course, there's another basically zero part corresponding to the kernel. All right, so for each of these non-zero finite dimensional eigenspace is inside E, and we potentially have countably many of them, but because T is compact, there are only countably many of these eigenspace. So we need some kind of approximation. So we cut it off to some finite dimensional ones, and we want to show that TF is going to be inside the closure of E. Okay, so that's what we're going to show. So we just observe the following. So let's start by if I take some f inside the continuous function of G, I can also think about f as in L1 and also in L2. So if I consider what happens to the TF, so just by the definition, it's quite clear to see why it's also continuous. And moreover, if I consider it's infinite norm, okay, so it's infinity norm, so that's going to be equals to the integral. So I write it as the little k of the, so it's just no other than the convolution of f with this kernel k. So I have k of y inverse x. I have the f of y, and then I have dy, okay, this whole thing to, well, the supremum of all of these values. And this k, I can, well, k here is fixed, so I can always make this k in the bounded, okay, so this is going to be less than equals to the infinity norm of k, multiplied by, well, you just integrate the f of y, so that's end up with the one norm of f, okay, but because your g is compact, you normalize your the measure of the entire g to be the probability measure, or if it's not, but it's just finite. So just by some basic measure theory, you know, the f1 norm is going to be bounded above by some constant times the f2 norm. Okay, if you normalize it to be a probability measure, it should be just less than equal to 1 times the 2 norm. So this is less than equals to k times the infinity norm times the 2 norm of f. Okay, so this infinity norm is going to be controlled. Okay, so this k here is fixed. So I want to prove that as the immediate corollary, I want to show that if you fix your k and you consider this TF, this Hilbert-Schmidt operator, that's going to be inside the closure of this E, okay? So the proof is really simple. So you do the spectral decomposition. So the L2 of G is going to be decomposed as a direct sum of some alpha, say alpha, let's just say index by some n. Okay, so n going from 1 to infinity of some h alpha I, h alpha n, and then these alpha are non-zero, and then you have one space for the eigen for 0, or basically the kernel. Okay. So your function f being in C of G, so it's also in L2. So you decompose as a summation of these. So for each one of these h alpha n, you have a copy. So let's say it's equals to ck or cn times some phi of n. Okay, and going from 1 to infinity. And then you, of course, on the h0, you also have, say, phi 0. Okay, so each of these phi n's inside h alpha n, so it's an eigenvector for the alpha n. And so because this is a L2 norm, so and each of these h alpha n are clearly orthogonal to each other. So the 2 norm of this f, okay, so that's going to be equals to the summation of these cn squared. Okay, so that's, well, and you should also plus the norm of the phi. And let's just say phi of these n are also normal. So let's say phi n is also normal. So this the 2 norm is going to be less than infinity. So it's certainly put an upper bound to your summation of these cn. Okay, and so And so if you consider what happens to these finite dimension, if you chop it up to these finite dimensional ones, so if you say t, evaluate on n going from 1 to some big N of the Cn phi n, okay, because each of these t evaluated on phi n is going to be inside E, and you take a finite sum, that's clearly inside E, okay, so that's for all n finite. So now if you pick some, so for every epsilon greater than 0, and you pick some large enough n so that the tail is going to be less than less than epsilon. So let's say the summation of these tails, C and phi n, this norm, and going from, let's say, n greater than this big N is less than epsilon. So you can always do that because your f is in L2. So what you can show is that if you evaluate t on this tail, so summation n going from 1 to n of the Cn phi n, I should say the tail, so it's the n greater than big N. Okay, so the infinity norm, we know that this is bounded above by some constant, basically bounded by the infinity norm of the little k multiplied by the 2 norm of the summation. And the 2 norm is less than epsilon, so this is less than the infinity norm of k, and times the epsilon. So k here is fixed, okay? I'm fixing 1k and consider this particular integral operator t. So I can see that the tail is going to be really small, okay? So what do I end up with is that this t of f is just going to be inside this E, okay? So I have this t of this f that's just equals to, basically is converging. So this I can find a sequence, let's say summation n going from 1 to this big N of C and phi n plus this phi 0. Well, phi 0 is in the kernel of t, so it doesn't really matter, okay? So I take the finite sum, and the tail is going to be small, so that's going to converge to the TF in the infinity norm, okay? So that just implies that this TF is also going to be inside the closure of the E bar, okay? So each of these is, we proved that from last time, is inside E, okay? So now we have a sequence converging to that, so TF is in the E closure. And now because of that, everything is kind of trivial now. So as an immediate corollary, we can prove the first version of the Peter-Weyl theorem. So basically, it just shows that the closure of E is going to be equals to C of G, okay, or E extends. Okay, so the proof is basically the what we already described. So you pick a K alpha approximate unit or approximate identity inside the C of G. So you can make them the symmetric, so you can make a K alpha x equals to K alpha x inverse bar. And then you construct a bunch of these Hilbert-Schmidt operators. So this T alpha f is essentially just f convolute with each K alpha. And each of these T alpha f is inside the closure of E, okay, by the proposition we just proved. And because these convolution, because they're approximate unit, so they're converging to f. So that just implies the f is also inside the closure of E, and so we're finished. All right, so this Peter-Weyl theorem is, well, why the density of E inside C of G is so important is that, well, there are actually a lot of nice consequences, okay? So let's just do quite a few of them here. So first of all, because E extends in C of G, so it kind of follows immediately that this E is going to separate points, okay? So basically for every G not equals to the identity, there exists a irreducible representation, let's say pi, such that pi of G is not the identity representation, okay? So basically it looks like the irreducible representation are going to separate points, okay? So think about, we actually have the same thing when we talk about when G is a billion, then the dual group, okay, we saw that this is essentially the Galfond spectrum of the commutative Caesar Banach algebra. And we use the Galfand theory to say that, well, the G hat is going to separate point. I just follow from the Galfand theory. Okay, so here is essentially a strengthened version for these compact groups. So the irreducible representation are going to separate points. It's not an entirely trivial thing, actually. So it takes some representation theory if you want to go the other route. And the second thing is that because the G is compact and the C of G is going to be dense inside the L2 space, so immediately you also have the second, so sometimes this is also called the Peter-Weyl theorem. So let's say part 2, okay? So you have the following decomposition of the L2 space of G. So your L2 space is just going to be isomorphic to decompose as a bunch of these E pi, okay? So here for each irreducible representation, you kind of do one equivalence, for each equivalence class, you have one copy of this E pi, okay? And so, well, because if two things are unitarily equivalent, then they give you the same E pi when you solve that. So for each equivalence class of these irreducible ones, you get one copy of E pi, and then you take their direct sum. Well, this is essentially just the closure of the E. Okay, so this is the closure of E, and we know because E is dense inside the L2. Well, so this is this L2 can be decomposed this way. Okay. And moreover than that, if you think about what happens to the left regular representation, so your left regular representation, lambda, is going to act on the L2 of G. And we saw that if you restrict the lambda on each of these E pi, this E pi is going to be a D pi square dimensional invariant vector space for this lambda. And we show that D pi, when you restrict it to this E pi, well, the lambda restricted to this E pi is basically D pi copies of the pi bar, okay? So you can really see this is just going to be equivalent to the summation of here, again, for each irreducible unitary equivalence class, you have D pi copies of this pi, okay? So this is essentially just D pi copies of them take the direct sum, okay? So you have D pi of them. So this is just proof is just really simple. The first part follows from the density. So E closure is inside the C, and if the C is dense in the L2, and the second just follows from our earlier result that if you restrict your lambda on each of these E pi, that's going to be unitarily equivalent to D pi copies of the pi bar, okay? Of course, you restrict it to the E of pi bar, you get D pi copies of pi, okay? So you do that. And it's also quite clear that if you do the right regular representation on the L2, it's also equivalent to basically the same thing. So that's also another proof that the left and right regular representation are kind of unitarily equivalent.